All right, welcome. Today we are diving headfirst into some of the biggest, most fundamental debates in all of science. We're talking about the huge intellectual battles that have literally shaped our understanding of reality itself.
So, let me ask you this. Does the future already exist? I know, it sounds like something straight out of a sci-fi movie, right? But it's a very real debate happening at the heart of physics. And to even start to answer a question like that, we first have to get a handle on the nature of our reality. So today, we're going to journey through 4 of these great scientific debates, starting with the very fabric of the universe, space itself.
Okay, so first up, what is space? I mean, really, what is it? Is it an actual thing on its own, like a giant empty box? Or is it nothing at all? For centuries, this has been a major point of conflict.
So on one side, you've got Isaac Newton's idea of absolute space. Just picture a giant, invisible, unmoving stage that holds the entire universe. It's just there. It doesn't matter if anything is inside it or not. But then, on the other side, thinkers like Ernst Mach and Albert Einstein argued for what's called relative space. They said, no, space isn't a container at all. Instead, it's just the web of relationships between objects. If you took away all the planets and all the stars and all of us, there would be no space left to measure.
And this quote, I think it just nails why that idea of relative space feels so, intuitive to us. We humans evolved to make sense of the world by comparing things, right? We use reference points. Is it hot compared to what? Is it far compared to me? We don't really perceive empty space in some absolute way. We perceive the distances between things.
So, who's right? Well, funny enough, it turns out both of these ideas are incredibly useful. For stuff happening right here on Earth, like figuring out how water flows through a pipe, Newtonian physics and its idea of absolute space is often way simpler and more efficient. It just works. But the moment we look out into the cosmos, if we want to predict the path of a meteoroid or understand gravity on a huge scale, Einstein's theory of relativity and its relative space is absolutely essential. You just can't get the right answer without it.
Okay, so we've debated the very nature of the universe. But that brings up a whole other question. How do we even decide which ideas are worth debating in the first place? And that brings us to our next big topic. How do you draw the line between actual science and something that just kind of looks like science?
This is a huge question. I mean, think about it. There are countless fields out there that claim to be scientific. You've got ufology, the study of UFOs. You got iridology, which claims you can diagnose diseases just by looking at a person's eyes. So how do we sort the real deal from just a good story? Well, let's look at 2 really powerful philosophical tools that can help us do just that. First up, we've got Karl Popper's brilliant idea of falsifiability. And here's the key takeaway, the real kicker. A theory is scientific not because you can prove it's right, but because you could, in theory, prove it's wrong. If there's no possible experiment, no observation you could make that would show your idea is false, then you're not really doing science. So let's take ufology, for example. The evidence is almost always based on someone's personal story, or maybe a grainy photo that can't be reproduced or properly tested. There's no experiment a skeptic could design to definitively prove the claim is false. So according to Popper's rule, because its claims can't be falsified, ufology gets filed under pseudoscience. But, okay, what if a theory is testable? Well, a philosopher named Imre Lakatos came along and added another really important layer. He basically said that a truly scientific field has to be what he called a progressive research program. And what that means is, it can't just explain things we already know. It has to make new, novel predictions that actually turn out to be true. It has to get better and more accurate over time.
Now, let's put iridology to the test with this idea. Take a look at this number, 51%. What on earth could that be about?
Well, check this out. In a controlled study, iridologists were asked to diagnose patients. Now, they correctly spotted gallstones in about half the people who actually had them, but they also said 51% of perfectly healthy people had gallstones. That's an accuracy rate no better than just flipping a coin. And this is a perfect example of Lakatos' point. Iridology shows no progress, its predictions aren't reliable, so, you guessed it, it's considered a pseudoscience.
Okay, so now we have some tools to spot what isn't science. But how does real science actually move forward? Is it this slow, steady, logical march towards the truth? Or is it something a lot more dramatic?
And that question is at the heart of another huge debate. Karl Popper, the falsifiability guy, he pictured science as the steady, logical process of just disproving old ideas one by one. But then a historian named Thomas Kuhn came along and said, hold on a second. He argued science actually moves forward in these massive, dramatic revolutions he called paradigm shifts. In his view, an old theory doesn't just get thrown out, it hangs around until a whole new one comes along to completely replace it. And that process, he said, can be messy and even influenced by human stuff like personal rivalries and social trends.
And the classic example of this is the story of physics itself. For almost 2,000 years, Aristotle's idea that the Earth was the center of everything was the dominant paradigm. It was just what everyone knew. But then the telescope was invented, and suddenly astronomers were seeing things, anomalies that just didn't fit the old model. Galileo's observations pointed to a new, sun-centered model, and finally Newton came along with a whole new set of laws of motion that completely blew the old Aristotelian view out of the water. That right there is a Kuhnian revolution.
But, and this is a big but, here's the catch with these paradigm shifts. Because they're social, they can get held back by plain old human bias. Galileo was put under house arrest for his ideas, a guy named Michael Servetus was actually executed for his theories on blood circulation, and Mary Anning's incredible fossil discoveries were ignored for years just because she was a woman. It just goes to show you that sometimes the dominant paradigm is defended not with better data, but with pure prejudice.
Which brings us to our last debate. And honestly, this one might just break your brain a little. We've questioned space, we've questioned science, we've questioned progress, so now, let's question time itself.
So, this whole thing really comes down to two wild ideas about time. The first is called presentism. This is the one that feels right to us. It's the idea that only the present moment, right now, is real. The past is gone, the future hasn't happened yet. But then there's eternalism, which proposes something much, much stranger, that the past, the present, and the future are all equally real, all existing at the same time in what physicists call a block universe. So from some cosmic perspective, your birth, you listening to this right now, and everything that will ever happen to you, it all exists simultaneously.
Okay, so what does the actual physics say? Well, Einstein's special relativity points pretty strongly towards eternalism. It shows that two people moving at different speeds will actually disagree on what events are happening now. And if now is relative, well, that suggests that maybe all moments exist equally. But when you get to the quantum world, oh boy, that's where things get really messy.
And this is where your head might start to spin. On one hand, you could argue quantum mechanics supports presentism. A particle's future is just a cloud of possibilities. Its past doesn't totally lock in where it is right now. But then you have these absolutely bonkers delayed choice experiments that seem to flip that completely on its head. They suggest that a choice you make about measuring a particle in the future can actually appear to change the path it took in the past. The idea that a future event can rewrite history? That sounds a whole lot like eternalism, and physicists are still scratching their heads over it.
And so, after all that, here's where we land. If space itself is relative, if the progress of science can be shaped by human bias, and if even the very flow of time isn't what it feels like, is everything up for grabs? Are there still absolute truths out there, somewhere, just waiting for us to find them? It's the biggest question of all, and one these great debates force us to confront. Thanks for exploring them with me.